Okay, now we get to the main concept here. I'll keep this running. Let's see if this terminates today. My sense is this is going to terminate maybe before the sun goes out, maybe after the sun, like, you know, in cosmic time scale, there will be a time when the sun is going to blow out. It's a star. Okay, you can take astronomy closers and they will tell you exactly when. This may not terminate by then. But maybe my computer will disintegrate, right? The atoms that make up my computer will not stay together and remain a computer, right? I would be long gone, for sure. All right, so why is that happening? So let's draw a picture and see why that's happening. So for that, I'm going to, so what's happening? So what's happening is Fibonacci of 10 calls Fibonacci of 9 and Fibonacci of 8. So let me draw this as a tree, and this is called a recursion tree. Okay, and Fibonacci of 9 is calls Fibonacci of 8 and calls Fibonacci of 7. This calls Fibonacci of 7 and Fibonacci of 6. Okay, and so on. So there's going to be a huge recursion tree that I am going to draw. And at the base of this tree, what do you have? You have the base cases. You have Fibonacci of either 1 or you have Fibonacci of 2. And these are going to be the base cases that Fibonacci is going to hit when called from a positive value. It's going to greater than 2. It's going to decrease, decrease, decrease until it hits 1 or 2. And then you're going to hit the base case, and then it's going to add up, add up, add up all the way to the top. And you can represent any kind of recursion abstractly by a recursion tree. Okay, and we care about two things in this recursion tree. We care about the depth of this recursion tree, which means like how many calls do I make in any branch before I hit the base case. Because once I hit the base case, that's the leaf of the tree. There is no more calls to hit. And so what's the worst branch? So what's the longest path that I have from the root to the leaf? How many nodes do I have in that path? And that is called the depth of the recursion, the depth of the recursion. So what do you think the depth of the Fibonacci recursion is going to be? So how long before you reach base case on any branch of this tree?
N plus 1.
N plus 1, in this case it would be 11. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So I think it would be n if I've defined the base case as, all right. Okay, so it would be n because we are stopping this particular Fibonacci at 1. If you had defined it to stop at 0, like I had done in my notes, it would be n plus 1. Okay, is that okay? It's just a plus 1, but this one goes from 10 all the way to 1. Is there a question? Yes. Okay, are we technically stopping at 2 or are we stopping at 1? This is a really good point. I think I may have messed up. In fact, it's slightly more trickier than that. So when you get to Fibonacci of 3 is when the action hits. You get two base cases, Fibonacci of 2 and you get Fibonacci of 1. This Fibonacci of 2 is actually a leaf. You just stop there. Okay, so the student made an excellent point, which is you don't actually go even up to 1, you just go up to 2. Or in some other branch, you skip 2 and you just go to 1. So if you are being extremely careful, you'd actually see that it's n. In this case, it's just n minus 1, in fact. It's just 9. Does that sit better with people who are a little bit more eagle-eyed than me? Okay? But, you know, in algorithms, we would say this is something like O of n or theta of n, however you want to call it. It roughly grows in the same rate as n itself. Okay? That's the depth of the recursion. There is another thing we care about. How many recursive calls do we make? How many recursive calls do we make? So count all the recursive calls, which means count all the nodes of the tree that you would encounter. Okay, and that's the number of recursive calls you would make. So Fibonacci, how many recursive calls do we make? Well, it turns out to be related to Fibonacci numbers itself. So it turns out that it's roughly the Fibonacci number of n is the number of recursive calls I make as well. Because the number of recursive calls I make for Fibonacci 10 is the number of recursive calls I make in this branch for Fibonacci 9, plus the number of recursive calls I make for Fibonacci 8 plus 1. So if you want to count the number of recursive calls, it almost is a Fibonacci number, except you have a plus 1. Okay? How big is that? We don't really need to know, but it scales roughly like 1.8 to the power n. So if you want to calculate Fibonacci of 50, the number of recursive calls you would make is about 1.8 to the power 50. If you want to make Fibonacci of 100, the number of recursive calls you would make is about 1.8 to the power 100. What's that number? Well, it's going to be an astronomically large number. That's enough for us right now. So anyone want to take a bet with me that the Fibonacci of 100 call is finished? Okay, so maybe if some space aliens came in and time warped us to like 100 or 1000 millennia from now, maybe that's okay, but it's not going to happen, right? So we know from math that it's very, very unlikely that my Fibonacci of 100 is not going to finish. So I just wrote a 3-line recursion, and I ended up like, writing something that's going to run for a really, really long time. So recursion is dangerous. If you are not careful with recursion, it's going to run for a really, really long time. Is that okay? Even though the advantage you see is that it's very close to how Fibonacci defined Fibonacci numbers, and how nice is it to write something that Fibonacci defined it this way. I write my code the same way. So nice, but it's also going to be dangerous because it's going to take a long time if I wrote the recursion this way. Now, of course, there is a trick here. If you took an algorithms class, you would notice that there is a lot of repeated work going on here. If you have already calculated Fibonacci of 8 here, then why calculate it all the way again? Couldn't you use this answer here, right? And there is a trick that you will learn if you have taken 3104 called memoization, which is storing previous results so you don't have to recompute them, but you can just access them. And when you memorize Fibonacci, it changes from this complicated algorithm to a much simpler algorithm. But I'm not going to worry about memoizing Fibonacci. Frankly, Fibonacci is not exactly the kind of computations we would like to do in this class, but it's still a warning that even simple recursion can be extremely expensive. Questions so far? All right. Not only is recursion expensive, it turns out that when I talked about termination of recursion, for things like Fibonacci, that's so much easier, right? Okay. That's so much easier to talk about termination. There are recursive functions whose termination is open even among mathematicians. And one very famous problem is called the collage function. So the collage function is defined like this. So a function is a function of n is 1 if n is less than or equal to 1. Okay? And the function is defined as f3n plus 1 if n is odd, and fn divided by 2 if n is even. It's a really, really simple function. It's called the collage function. And the point is, you can write this collage function as a recursion. So let me show you how. Get back to sharing my Jupyter notebook here. Okay, share that. All right, make it. Okay, still not going to finish. I give up. By the way, we'll come to this in a second. What is this? We'll come to this in a second. It just dumped the stack. Okay, so this is called a stack dump. And I'll talk about that in a second. I'll talk about stack overflow, which is another problem you can have with recursion. All right. So what's the collage function look like then? So the collage function looks like this. So define collage. So how do we do it? We say if n is less than or equal to 1, then it's just 1. Else, I'm just following the definition I wrote. I wish I could fetch it in a second, but you can always like, I'll post the video, you can see it. If n is odd, then it's the same as collatz 3 times n plus 1, else it's the same as collatz n over 2. Okay, and let me for fun just print in Scala. This $n is called a macro expansion. It expands to whatever n is inside the string, and to trigger a macro expansion you put a s in front of the string and that macro expands. Okay, this is useful in Scala. I don't like writing format strings, so I can always do macro expansions. So this is collatz. So what happens if I do collatz on 100? So you can see this 100 calls 50, calls 25, calls 76. It keeps going for a long time, but eventually it reaches 1 and exits. So the collatz conjecture is that this collatz function on any n always terminates, always ends up reaching the base case. But the argument is not simple. You're not making progress towards the base case. You're kind of jumping around, but eventually somehow you do get to the base case. Why? No one knows. This is open for more than like 80 years now, right? So it's an open problem in mathematics. Recently there has been some progress on it. So if you Google collatz function on the web, you will see that there has been some breakthroughs on it. Recently they proved some really cool result on this. Doesn't escapes the top of my head, but I'll post a link on Piazza if you're interested. So proving termination can be dangerous. Okay, so most of the time when you write recursion, hopefully it's not the collatz function, but it's some tame recursion, more like the factorial function. All right, let me then talk about recursion in terms of two things, right? So the stack depth of recursion and the number of recursive calls. So you need to worry about both stack depth and number of recursive calls. Okay, and I'm going to talk about how recursion is implemented. Before we do that, I'll just add that recursion is not necessarily just for the simple things like numbers and so on. You can do recursive function on strings. So for example, I asked you in your assignment 1 to write is palindrome function recursively on strings. Okay, so that's an example, right? And last lecture I showed you how to count the number of matches to a character, like using a while loop or using recursion. So we've been playing around with recursion. So you know that it's not just numbers. It can be used for numbers. It can also be used for strings. You can also do it for lists. And in the rest of the class, we'll drive this point home by exclusively writing recursive code. Okay, so now let me talk about how computers implement recursion. So what is this business of the stack in a recursion? So I'm going to draw a picture and talk about that. I'm going to show you how recursion grows the stack and how this can be a problem, okay? And then I'll show you a very benign form of recursion called tail recursion, okay? And there is something called tail recursion or tail call elimination, which we'll talk about, which compilers do, which makes tail recursion particularly benign, almost the equivalent of writing a loop. So I'm going to talk about those two things next. Before that, any questions? Nope? Okay. This should be simple, right? I'm not really doing something complicated here. Even if you haven't seen recursion before, hopefully it doesn't really, boggle your mind. So I hope that's okay. All right, so let's get back to this business of recursion. So let's write a simple recursive example. Let's go back to our factorial function. So we had this factorial function. I'm not going to write all the types. You can fill them in. So if n was less than or equal to 1, then it was 1, else it was n times factorial n minus 1. So how is recursion implemented inside a computer? So inside a computer, any function call has to have something called an activation record. So function calls have to have something called an activation record. And it's associated with every function call. So every time I call factorial, it creates an activation record. Okay? And in this activation record, I have some information that's needed for me to execute the function. So what's the information that's needed to execute the function? So the key information is what's the value of n in my current call. So because this n is the parameter, I need the value of n. Okay, I need to know that in my activation record. I have to store the value of n. I store it in my activation record. If I have any local variables, so if I have val x equals 1 in my code, for some strange reason I want to do that, then I need the value of x. So let's say n equals 10, x equals 1. Okay, and those of you who have taken 2400 should be familiar with this in more details than I'm talking about right now. Okay, but there is also something else you need to store, the return. In a very low level sense, you need to store the return address, the function, the callee who called me, who's waiting for my answer. Right, you need to store that. In this case, we'll just keep it abstract, right? So we'll just say this is the, abstractly, this is the caller, the function that called me and caused this activation record to be created. Okay, and so activation record stores the data, okay, that's associated with executing a function. If you have taken 2400, this should be clear, this should be something you've seen before. If you haven't, this is fine. You know, this is enough of something to know. And computers, you know, organize their memory in two different regions, okay? Again, this is 2400. You will learn this there in much more detail, in like very gory details. But for now, there's two parts to the memory. There is the heap and there is the stack. Okay? And activation records live in the stack. So typically the entry point of a program is a function called main, typically. So you would have the activation record for main at the very bottom of the stack, because it's the thing that's going to call everyone else in the program. So if main calls foo, there's going to be an activation record for foo, but that's going to be above the stack on main. And if foo calls bar, then bar is going to be above the stack on foo. If bar calls who, then that's going to be above the stack on who. I don't know who names their function like who. Anyway, bad joke, apologize. Keep moving. Is that okay? All right, now what about the return address? So who is, by the way, going to have the return address of bar? Bar, it is going to have the return address foo. Foo is going to have the return address for main. Is that good? This is being extremely rough. You are going to be much more fine-grained and precise when you take your systems class, because there you will know exactly not just the return address, but where in the function do you return and all that. Okay, so not going into that. All right, and of course your microprocessor, if you're using an Intel chip, you know, they have mechanisms by which you can make the activation record easier to store, access, easier to fetch. You know, you have instructions that can work with your activation record. You know, there is a ret instruction that will take the return address from your activation record and return there and so on. Right? There's a call instruction that will create things for you. Okay, so let's not get that detailed. Okay, let's just say abstractly there is this structure that's being built up. As you keep calling more and more functions, you're piling them one on top of another in the stack. As functions return, their activation record gets destroyed. So when main calls foo, when foo calls bar, and bar calls who, and then when who returns, whose activation record gets destroyed, and now you come back to the activation record of bar, and maybe you update some variables there and you keep going. Is this picture clear enough? Okay, so now comes recursion. So what does recursion do? So what does a recursive function like this factorial function do for us? Well, it's going to create a pile of activation records one on top of another, right? So as an example, let's talk about factorial 10. And let me erase all this mess here so I can keep drawing a bigger mess. All right. And by the way, what is stored in the heap? Do you know? So I said activation records are stored in the stack. Do you know what is stored in the heap? dynamically allocated memory, global variables, they are stored in the heap. Of course, Scala doesn't have global variables. Scala does have dynamically allocated memory. All those new operators are dynamically allocated memory. And those would be stored in the heap. Okay, so heap and stack, two different regions of memory that computers, I mean, this is convention, right? This is not like decreed from above, like thou shalt have a heap and you will create a stack and you will grow the stack. No, no, no. I mean, this is all human convention, right? This is how people who designed like the first microprocessors and the C programming language, this is how they decided to roll, and this is how we roll, right? It's not set in stone, and obviously you can change it. But no one's bothered because it works so far. Yes, question. Does Scala support garbage collection? That's the question. That's a really good question. Yes, it does. Otherwise, it would be really difficult to write a language like Scala. The rest of you may be wondering, what is garbage collection? Well, it's the thing that comes on Tuesdays and collects the trash from. No, it's very similar to that. It's basically that, you know, there are many languages where you have ways to allocate memory, like new. But in Scala, there is no way to delete memory. There's no delete in Scala. You can allocate memory with new, but you don't need to delete anything. So what happens is magic. Well, garbage collection. What happens is the runtime environment figures out that you are no longer needing access to a particular point in the memory, and it automatically frees it for you, or it deallocates it for you. So you don't need to do any kind of delete. You just do new. Okay? How do I get that, you know, fancy thing in C++? Use something called smart pointers. In fact, that's what you should be using if you know what's good for you. Okay, that's what I always use. I never use raw pointers. It's not worth the amount of time you spend in front of a debugger, so use smart pointers, and that's called garbage collection. Are we going to study garbage collection in this class? I hope so. We get very close to it, and so hopefully we'll study a toy garbage collection algorithm for the language we'll design. We'll get to it very, very late in the semester. No worries for now. Okay, good question though, very good question. A little bit ahead of time, so don't worry, we'll study garbage collection when the time comes. Let's go back to this factorial business. What does this activation record look for? Factorial 10, maybe I'm getting too ambitious in my, yeah, let's do factorial 4, good enough. All right, so what's factorial 4 going to look like? So now you have your caller main, and let's say main is going to call factorial 4. So the activation record for factorial 4 expands like this. So n is 4, x is 1, so on and so forth. And you would have some other data there. And the return address is who called me, let's say just main for now. Somewhere inside the code of main is the return address. Now what happens when factorial 4? Factorial 4 is going to now call factorial 3. Right, and here n is 4, n is 3, x is 1. So this is the activation record for factorial 3, which is going to call factorial 2, which is going to call factorial 1, and eventually you get to factorial 1, and factorial 1 hits the base case. You're not going to have any more recursive calls, so this is going to return the value 1 to its caller. Okay, so everyone okay so far? With factorial going all the way down to 1, each time you make a new call, you're growing your activation record. And each time factorial 1 returns, it gets out of the stack and it's going to return 1. Well, factorial 2 is going to use this. It's going to do this computation, multiplication, and then it's going to do factorial 3. You're going to return a value here. That's going to return a value to factorial 4. That's going to return a value to main. So stack grows, stack empties, get back to main with a value. Okay so far? Now obviously one of the problems is if your recursion, how big does your stack grow, by the way? For a particular recursion, how do you know the depth of your stack, the maximum possible depth of your stack at any instant in time? How much will that be in terms of the recursion tree? Well, it would be the same as your recursion depth, which is why we care about it. Okay, so the recursion depth is basically going to bound how big your stack grows. So how much stack memory is your recursion going to take up? And so you've heard the term stack overflow. So tell me, why does stack overflow happen? Because your recursion got too deep, right? You created too many activation records in your stack, one on top of the other, that the total allocated memory for stack size just blew up. Because, obviously something like the Java virtual machine, which is going to manage your stack, is not going to allocate like infinite amount of memory. It's going to say, you get to use like 1 gigabyte of stack if your computer has like 8 gigabytes to offer, and you can change this setting. There are settings you can change to increase the JVM stack size. But at some point, you're going to hit the ceiling of your stack memory, and you have no more stack to allocate. So if you have no more stack to allocate, you have no more recursion to do, because where is your activation record going to sit? You don't have any more memory left in the stack, so you give a stack overflow message. Okay so far? All right, so that's the problem with stack overflow. All right, now comes this idea of a particular kind of recursion for which you don't need to grow the memory in the stack. And this is called a tail recursion.